Okay, so now we are going to go through, let's say, light cone. It's also called light front. It's also called equal x plus uh, quantization. Okay, um, so this will give you an idea. It'll be a concrete example of a situation where we don't take the parameter t to foliate spacetime. So if we were in d dimensions, x mu, we would have x naught, that's time. Then we would have x1, x2, and going all the way up to x d minus 1. So there are d minus 1 spatial coordinates. And then we're going to introduce light cone coordinates. So this is x plus minus, and x plus minus is defined by x naught plus or minus x d minus 1 over square root of 2. So there are two coordinates. And then we would also use xa, where a goes from 1 up to d minus 2. Good. So in a light front quantization, we would use these coordinates in the green box. Just a different choice of coordinates, no big deal there. And we would study the x plus is equal to constant slices. Okay, so this is the picture that we want to develop. So rather different to saying equal time slices. So just to give you some small idea, and we'll try to develop things as much as possible. So here is x naught, there is x1. And you know exactly what the equal time slices were. The equal time slices were these horizontal slices that collected all of the events at the same time. So that's what we would have done in the equal time quantization. Now let's talk about what we will do in an equal x plus quantization. So now we want to set x plus equal to x naught plus x d minus 1 uh, over the square root of 2 equal to some constant. Okay, and sorry, let me just change something. I want this to be x d minus 1. So if we now solve for x naught would be equal to minus x d minus 1. So it'll be a line of slope minus 1, and then it will be plus some constant, which I will call c. So c is a constant, and these are the lines of constant x plus. So if we sketch the lines of constant x plus, they are lines with the slope of minus 1. So it looks something like this. And the constant c would tell you exactly which slice you're on. And now it's these slices to which we would associate a phase space if we were doing classical physics, or we might associate a Hilbert space or a Fock space. So these are our equal x plus slices. So this is the first thing that changes. We're foliating space-time in a different way. Now, what I want to do is, so let's study, let's for concreteness, okay, this works in any D, but I'm going to work in D is equal to 4, and I'm going to study the simplest theory I can, which is a free, massive, scalar field. So that's perhaps one of the simplest theories that I can think of. And let me just say a reminder over here. So I want to remind you a few things about this theory before we do the equal x plus theory. So what do we have? We've got the Lagrangian, which would be to take the form of 1/2 d mu phi minus 1/2 m squared phi squared, and we're working in d is equal to 3. If we write this out explicitly, I mean, I'm sure you know this, but let's just make sure that we're all on the same page here. We've got minus 1/2 d1 phi squared minus 1/2 d2 phi squared minus 1/2 d3 phi squared. So that would be the kinetic term. And then, of course, we've got minus 1/2 m squared phi squared. What would we have for an equal time description? Well, our conjugate momentum pi of t comma x, this would be given by taking a derivative of the Lagrangian density with respect to phi dot of t comma x. And, well, that's just going to be phi dot of t comma x. So that's what the conjugate momentum is. We can also ask what is the Hamiltonian. So the Hamiltonian would be an integral d3x of the Hamiltonian density, and the Hamiltonian density is nothing but phi dot. So it's the momentum conjugate to phi times phi dot minus the Lagrangian density. And if you work this out, so please do check this, but it's a very simple calculation. This is 1/2 pi squared plus 1/2, and then we've got the gradient of phi dotted into the gradient of phi. The gradient of phi only has spatial derivatives, and then we've got plus 1/2 m squared phi squared. And then finally, what would we do to quantize the theory? So to quantize the theory, we would impose the equal time commutation relations, and this is how they read. So it's the commutator of pi and phi, both fields taken at the same time t, because we're doing an equal time quantization. We've got a minus I h bar, and then we've got a delta of x minus y. Good. So this is just a reminder of all of the formulas that we would have written if we were quantizing the free massive scalar field in d is equal to 4 using an equal time quantization. Now, let's write down the formulas for a light front or equal x plus quantization. Okay, so now I will go back to black, and this is now equal x plus. So x naught is equal to x plus x minus over the square root of 2. So you can see that obviously that's the case from our definition of x plus minus given over here. If we add x plus to x minus, we just get x naught over square root 2. If we say x plus minus x minus, we will get x3 over square root 2. And x3, because we've set d is equal to 4. So x3 is equal to x plus minus x minus over the square root of 2. Good. So we know how to define the light cone coordinates in terms of the normal coordinates, and we know how to write the normal coordinates in terms of the light cone coordinates. So now let's look at derivatives. Well, if we take d by dx plus, as usual, now we're going to use the chain rule. So if something is a function of x plus, this means, actually, let me put in our formulas over here as well. So insert space. I'll move that down one more. And let me just put in x plus is equal to x naught plus x3 over the square root of 2, just so that we've got these here to refer to, x naught minus x3 over the square root of 2. So if something is a function of x plus, it is a function of x naught and x3. So we can say by the chain rule, this is dx naught dx plus d by dx naught plus dx3 dx plus d by dx3. And then the good news is we've got x naught and x3 above. So we know that if we differentiate x naught with respect to x plus, we'll get 1 over the square root of 2. And if we differentiate x3 with respect to x plus, we'll also get 1 over the square root of 2. So this is d naught plus d3. So just a simple application of the chain rule. A completely parallel argument shows you that d by dx minus is 1 over square root of 2 d naught minus d3. That minus sign coming because x3 is x plus minus x minus over the square root of 2. Great. We'll continue in a moment.